that are, the first is transversal symmetry, the second is the particle hole symmetry, and the third is the chiral symmetry. Depending on the presence or the absence of these three symmetries and the dimensionality of the system, we have different classifications for topological insulator, actually, and maybe topological superconductors. So here, please note that this is about the topological insulators. I mean those systems that has gap, and depending on what I mentioned, we have different classifications. So here I want to say that what would be the concept of these three symmetries when we are looking in the band at the band structure. I mean, at a glance, looking at the band structure, how we can interpret these three symmetries. The first one is the transversal symmetry, and if we look at the band structure of the system, then for a state, for example, here in a defined K point, the other state that is equivalent to the minus of the previous K point, in this way, the relation between these two states is applied by transversal symmetry. The other one is the particle hole symmetry. For the particle hole symmetry, we should note about two things. One is to connect the K point to the minus K point, and also the energy to the minus energy, not just the K to minus K. So based on this explanation, the formal mathematical relation comes here in this way. So this one, I mean the particle hole symmetry and the transversal symmetry, these two actually are comprising from anti-unitary operators, and the other one that we may write it as the multiplication of the transversal symmetry and particle hole symmetry is called the chiral symmetry. And in the chiral symmetry, for each K point, we connect to the same K point of the state, but with minus energy. I mean, this way, here this state is connected to this one at the same K, but with a minus energy. So if we say that a system has a chiral symmetry, we are saying that if we have a positive, for example, E in the energy spectrum, we equivalently have the minus energy in the spectrum. So in this way, we can say that the system has a chiral symmetry. So this is a kind of just pointing out that what is different symmetries in the classification of topological materials. So as I mentioned, depending on these different symmetries, the topological class is different. So here, I want to focus on this one. I mean, if the system has this kind of behavior, then we want to understand the behavior of those systems and to better to have a better understanding of the concept of chirality here, this kind of energy spectrums or band structures. Okay, so before going ahead and focusing on the solid state systems, I mean SSH model and the Graphene model, I would like to firstly give some information about the concept of chiral symmetry, what I mentioned in the context of the particle physics. And here I want to start from the very famous Dirac equation that has this form. In quantum field theory, this equation describes the massless particles. And here in this equation, these gamma matrices obeys this algebra that is called the Clifford algebra, and we have a sort of anti-commutation relations here, and each of these gamma matrices obeys this relation, this anti-commutation relation, if we have a different matrices, something similar to what we have in Pauli matrices and the anti-commutation relation there. So here, because we considering the spin of the system in the space-time, here these gamma matrices has a 4x4 dimension, and equivalently, firstly we define 4 gamma matrices as this, and the Dirac equation itself, puts some constraints on the behavior of these gamma matrices, and when we want to satisfy these constraints, there are a lot of choices to define these gamma 1, gamma 2, gamma 3, these matrices. So I mean, there is we can say that there is not just one way to define these matrices. There are many ways. So a very famous representation is called the chiral representation. And in this representation, the form of these 4 gamma matrices is given by these relations. And if we substitute these gamma matrices in the Dirac equation, then we can rewrite the Dirac equation in this form, and using the equivalent expressions of these terms in the equation, we can finally, in terms of a while spinner that is defined as a up and down, maybe left and right blocks, which is called the while spinner, we can rewrite the Dirac equation as this expression. So you see here some expressions in the language of the Pauli matrices is appearing in this equation, and also here this M actually describes the mass term in the Dirac equation. And if we finally simplify this equation, we arrive at this final expression, here you see that the right and the left blocks of the wave function or parts of the wave functions using the mass term in the right hand side of the equation is mixing. So if we have a mass term in the Dirac equation, the mass term will mix the states, these right-handed and left-handed states. But in the massless limit, we have two quite independent equations. So here we can say if we have massless limit, then the right-handed and left-handed equations will behave quite independently and will be separated. And we can say that there is something here that is responsible for this right-handed and left-handed behavior. And the question is that what is that operator, or what is that symmetry? And the answer in the quantum field theory is that we have another extra operator here that is called the chiral operator. So in the context of the quantum field theory, as I said, if we have an even dimension, for example, here 3 + 1 dimension, it is shown that for this case, another extra operator that is called chiral operator is defined. And in the chiral representation, in that representation that I mentioned, the explicit form of the chiral operator is something like this one. And if I apply this chiral operator on the Weyl spinor, like this one, then we can see that the effect of this chiral operator is something like this one. And if I go ahead and rewrite this term by adding a unitary operator, finally I can write the left block as a this expression. So here we can say that this term, this multiplication, shows a kind of projection operator for obtaining the left block, and this one is the projection operator for obtaining the right block. So here, by this definition and using the obtained projection operators, if again I apply the chiral operator on left and on the right blocks, finally we can see that the chiral operator is an eigenstate of the left block with a -1 eigenvalue, and the chiral operator is a kind of eigenstate of the right operator with a +1 eigenstate. So overall, we can say that the chiral operator here selects different left-handed and right-handed states in the total spinor. So I mean, the chiral operator here is functioning, is acting like a selecting operator to give the left-handed state or right-handed state. So in this way, we can understand that what is the meaning of the chirality and what is the meaning of the chiral operator. So in summary, I want to say that chiral operator selects right-handed and left-handed states in the Dirac equation. So another thing in the context of the quantum field theory is this algebra that here I defined. So I want to emphasize on this algebra and the concept of selecting left-handed and right-handed to make the connection with the concept of chiral symmetry inside the state. That why we call the chiral symmetry or sublattice symmetry in the context of the solid state and condensed matter that way. So another important thing in this equation that I showed here is that we may rewrite that equation in this way, and in this way. So if we define a new operator that is called the helicity operator that has this form, in the massless limit, this helicity operator and the chiral operator gamma 5 that I defined shows the same behavior from the point of view eigenvalue and eigenvector. So in the massless limit, we can say that the helicity and the chiral operator are the same or equivalent. So
the chiral eigenstate is the helicity eigenstate.
Yes. In the massless Dirac equation.
In the massless limit.
Massless limit, yes.
Yeah.
So what maybe one ask that what is the concept of helicity operator here? Helicity operator here says that is the spin or the momentum parallel or antiparallel? Due to this interaction, it describes that the spin of the system of the particle and the momentum are parallel or antiparallel. So in this way, we can define the helicity. Okay, so yes.
So
yes, for sure. Yeah. The form of the operator is quite clear here. You see, here. Let me show you. Here, this is a matrix, something like what we have, for example, in Pauli matrices, something like that. And this gamma 5 matrix can transform the state, okay? A Dirac state. So here I have shown that how it can, for example, here, how it can transform the state. Do you understand this part? Okay. Let me.
So one word, Esmaeil.
Yes.
One word. Not only one 3+1 dimension, every even dimension Dirac fermion, every even dimension Dirac fermion theory, we can define the gamma 5 that is all anti-commuting the pre-existing the gamma 0, gamma 1.
Yeah, exactly. For example, in 1+1, we can just define the gamma 0, gamma 1, and gamma 5. Three matrices.
Okay, and the gamma 5 in the massless case, we always can define the gamma fiber eigenstate left helical and the right helical. Okay, okay, please
Yeah,
go
so
ahead.
I'm answering the other question.
Oh,
So here,
okay.
this is the very clear explanation that how will the gamma 5 operator will act on the state, okay? But here the definition of the helicity operator is something different. It's the multiplication of those another matrices actually with the operator. Okay, so it's different, but in the massless limit, I said that it is shown that the eigenvalue and eigenvectors are the same. Yeah.
So
So
in particle physics, the helical number +1 or -1, as Ismail wrote here, psi r and psi l. This helical number is a particle character of a massless particle. Well, seemingly, it has been believed that the character of a neutrino, but actually there was some discussion of some violation of anything. Okay.
okay.
Mm.
So no, the question is that when we think about the even dimension and in relation to what I said, what kind of interesting physics maybe appear in the context of the condensed matter and topological materials? And the answer is that if we again rewrite the Dirac equation in the language of the a Dirac-Lagrangian, and if we in addition to the free particle limit, we consider the coupling with a gauge field, something like this one, then the new shape of the equation will be this one. And similarly, I said that because of the dimensionality, I mean the even dimension, here in addition to the usual vector symmetry here, this vector symmetry actually transforms the state as usual. There is no spatial difference, but for even dimension, another extra transformation or extra symmetry we can define in connecting with the gamma 5 that I mentioned, and that is this one. And for each of these transformations or symmetries, the first one is called vector symmetry. The second one is axial symmetry. For each of these two, we can attribute the corresponding currents, vector current and the axial current. And it is shown that in the massless Dirac limit, the continuity equation is hold for both of them, for this one and for this one. For in the classical field theory, it's okay, no problem. But if we think about the massless limit, but when we want to quantize the theory, I mean, when we want to treat the problem using the quantum field theory, something like that, the previous continuity equation for the first one, I mean, the vector current is satisfying again. There is no problem. But for the axial current, some extra terms is appearing. In addition to this one, this term here is when we consider the mass. But if we consider massless term, already I removed this one because this comes from the mass term. But if we think about massless limit, and we think about the quantization procedure, then it is shown that extra terms will appear. For example, in 1+1 dimension, due to the gauge field, this term is appearing, and in 3+1 dimension, this interaction term is appearing. So these two terms are acting like a source of the current. So this, because this is it is not a usual thing. People usually call these terms as the source of a kind of anomaly. So here the concept, I mean the summary of the concept is this. When we can define the gamma 5 chiral operator, then it is shown that we attribute a kind of unusual source of current in the massless limit of the Dirac theory, and it is called the anomaly currents. Okay, so these anomalous terms in the topological properties of materials has a major role, has a very important role for different properties of those materials. For example, this interaction that is equivalent to this one, E dot B here, is the source of many unusual or topological properties. For example, if we focus on the static response in the topological material, then this term can be the source of some properties like a topological magnetoelectric effect, and that is related to a kind of dynamic that is called axion electrodynamic. I mean, this term is related to this action term via the action term like this one, and that is the origin of the property of magnetoelectric effect. And also it can gives rise or result into the appearance of something that is called Fermi arc in Weyl point in three-dimensional materials. Also, there is a dynamical response. I mean, this one can be predicted using the static calculations, and we don't need to think about the dynamical version. But there are also another effects, and one of the main effect is called chiral magnetic effect. And also it is related to this anomalous current that here I mentioned. Overall, I want to say that the chiral operator that we had in the quantum field theory can be emerged in the context of the condensed matter. So let me come back to the concept of chiral symmetry now in the SSH model and the Graphen model. again, if you remember, I can summarize the Hamiltonian of a SSH model and the graphene system. For example, this one is a one-dimensional, this is two-dimensional, and overall I can rewrite all of these Hamiltonians, the type bonding Hamiltonians in the reciprocal space like this one. And so finally I can say that this has this final form using the Pauli matrices. So similarly, here, if we don't have a master, something like what I mentioned in the quantum field theory, here there is a similar algebra to what I said in the field theory of the Dirac equation. And if we define this operator, the sigma z operator, like this one, we can do everything very similar to what we had in the quantum field theory. But here, instead of thinking about right-handed and left-handed states, we think about the contribution of the sublattices A and B here. I mean, if we define this operator like this one, this operator may, in a similar way to what we had in the quantum field theory, will distinguish between the different sublattices, the sublattice A and sublattice B. So if we do everything very similar to what we have had in the quantum field theory and the gamma 5, if I define the gamma here like this one, this is equivalent to what here I had, something like this one. Please keep this page in your mind, and everything here is similar. Everything is here is similar. I mean, the philosophy of the algebra things is very similar. So here, if I define the gamma operator like this one, and if I think about the anti-commutation relation as this, and then instead of the chiral representation, if I say I have a sublattice representation, explicitly writing this Pauli matrix as this one, then the effect of this operator on each components of the eigenstate, I mean the contribution of A sublattice and B sublattice, will be very similar to what we had in the quantum field theory procedure. So finally, I can, very similar to that, define the projection operator like this one and like this one, and we can say that the role of the gamma operator here is to select the sublattice A with a minus eigenvalue and the sublattice B with a plus eigenvalue. Okay, so because of this similarity, usually people call this operator as chiral operator. It's a kind of nomenclature, something like that.
Yes.
Yeah, actually, maybe the better name is to just say sublattice symmetry, not chiral, because I'm thinking that the chiral symmetry is somehow misleading here.
Okay.
Yeah. So I mean, because everything goes ahead, similar to what we have in the Dirac theory, people usually call this symmetry as the chiral symmetry. So, and that's it. And I want to say that in this way, the role of the chiral symmetry is to just select each to distinguish the contribution of sublattice A or sublattice B, and in similarity with right-handed and left-handed, we call it chiral symmetry or sublattice symmetry. So there is nothing more here to think about. For example, attributed current or these things. Just similarity between the algebra procedure causes to say it chiral symmetry. That's it.
Okay. Okay. So would you go back? Go back? Yeah, here. So the last question.
Yes.
Okay, good. So for this part, let's question the difference between the massless, well, not necessarily massless. Let's question the Dirac Hamiltonian or Lagrangian Dirac particle and this graphene.
Yes.
In the Dirac particle case, this this one, this Hx and Hy. In the Dirac particle case, they are linear in momentum, just a p, just a k. So in that case, this sublattice symmetry actually very analogous to the chiral symmetry and kind of the the uh, the chiral eigenstate here can be defined, but in the graphene model, we don't think of a Helicity number because the Hx, Hy, they are not linear in K. But if the Dirac particle Hx, Hy, Hx, K is just Hxk, this is just a Kx, and Hky, this is Ky. In that case, we can define the helical number.
Yeah.
Okay. So but the value approximation, for example, in the K-Valley, value approximation, you know the Kx, sorry, I don't have a mouse. Value approximation, we can very near to the value approximation, we can approximate the graphene Hamiltonian into the linear form. There, near the valley, we can define the Helicity number. So in the K valley, we have left helical state, right helical state. In the K prime valley, we can have a left helical eigenstate, right helical eigenstate. But the K valley, left helical eigenstate, right helical eigenstate. K prime valley, left helical eigenstate, right helical eigenstate. But they are kind of they are switched. They are switched. Valence band, conduction band, they are switched this way. So the difference is that Ismail, do you understand what I'm talking about?
Yes.
Oh, okay. So if ever we can linearize this Hamiltonian, after linearizing this Hamiltonian, we can people make the analogy with the Dirac particle near the Dirac cone, So there near the Dirac cone, we can define the Helicity number for the massless Dirac particle. And would you go back to the page 11? So here, yeah, here, sorry. Yeah, here, in this page, Esmaeil summarized that Esmaeil, would you go back to the U1 symmetry and the chiral symmetry, the page you summarized the symmetry. Yes, here,
This one?
here. Yeah, here. So the Lagrangian, or the action integral is invariant over the global U1 symmetry, you call the vector symmetry. Alpha must be constant. The global U1 symmetry or global axial symmetry, would you go back to the page 11? Then the conservation current, notice conservation current, we have a vector current conservation and we have a axial current seemingly conserved, but on the quantization, classical field theory, it has conservation, but on the quantization, it has somehow strange way, anomalous way, it is broken. So this anomalous way of breaking is E dot B. So let's say that when electric field and the magnetic field in the same direction, E dot B, it is kind of something strange, but in the quantum field theory context, why this one appear, why this one is called the anomalous way. It is somehow really strange. The anomalous way means that it doesn't appear in the classical field theory. It only appears in the quantum field theory. But let me, the Abba. Hello, Abba. Yeah. Do you have any question for this presentation? No? Yeah, actually, Ismail showed the connection, try to explain. Ismail, would you explain again the kind of analogy, connection of the massless Dirac particle and the condensed matter physics, how it is related? Would you try again? Explain again.
Maybe the let me show you here this one. Maybe the best starting point is here. No, we can if we rewrite everything of the Dirac point, massless Dirac point in the quantum field theory. Finally, we arrived to this one. Actually, this one is when we have mass, and in the massless limit, finally we have this equation. Okay, so this equation is very similar to the low energy Hamiltonian of something like graphene system. I mean, if you,
yeah, so
yeah,
Ismail here, would you make one or two more pages that here, think about, let's compare, maybe, yeah, let's compare this Hamiltonian, sorry, no. After this meeting, would you please, this
okay.
compare, yeah, would you compare this, let's say that, would you compare this Hamiltonian with the graphene's Hamiltonian HXHY? This Hamiltonian is really linear in momentum. Graphene,
Yes,
anybody does that near the Dirac cone, HXHY linearly approximate. In that case, it is very analogous to the massless Dirac particle near the cone, K valley and the K prime valley. So
yeah,
would you kind of make one page for this context?
yeah, I see, yeah.
Okay.
No, but actually, if we consider the dispersion of graphene near this K point, yeah, this is, for example, the K point. Around this K point, we can rewrite, let me show you. We can rewrite this general form as something like this one, sigma x, so something like this one, okay? Ky, sigma y. So something like this one. Around that K point, the Hamiltonian around this K point is described by this form. And this is very similar to the P dot sigma term in the Dirac equation. Okay, so they show a very analogous term, and in this way, maybe we can define around the K and K point. Maybe we can define different helicities for K and K prime valley. Yeah.
Okay. So please go back to the page 11. So let no, maybe page 12.
Well,
Yeah. So let's please keep in mind, let's remember this is the strange source, the anomalous breaking, strange way of breaking of a chiral symmetry, chiral current. This one. Let us please remember. And let me share my screen. Let me share. Ismail, would you give me the option? Let me share my screen. Do you see my screen?
it is sharing.
Do you see my screen?
Yeah.
Yeah. We are calculating the current and the orbital and the spin using the TDDFT time-dependent density function theory of the chiral wire. You see the left-handed wire and the right-handed wire. And we have a very interesting result that, for example, these two systems, if we have the same left-handed wire, right-handed wire, sorry, the same wire, this both right-handed wire, if we apply the B field up and the B field down, and also the same way, um, the the same chiral wire, we can apply the E field up E field down, something like that, or we apply the opposite chirality, left-handed and right-handed, and we apply the the electric field and the magnetic field, and we understand that when you apply the my page is noisy. I'm just sketching my idea. Suppose we have two wire in our system. Suppose we have a two wire. Let's say that we have a two wire. So let's call it this is let's call it, let's give a name that this is a chiral asymmetry, chiral broken system. And let's say this system is a chiral symmetric system. Our system has exact chiral partner. Let's call it, our system is a chiral symmetric system. Okay. And this is a chiral asymmetric system. Esmaeil, do you agree? Do you understand? Do you agree my language, my definition?
Yeah.
Okay.
We already had a discussion about this.
Okay. Now, Abba, do you agree? Do you understand what I'm my definition of language? Okay. Now let's look at this chiral symmetric system. Chiral symmetric system. So in this chiral symmetric system, just a moment. Chiral symmetric system, let's apply electric field. Our TDDFT calculation tells that when you apply electric field, this part develops a current up, and this part develops a current up, but this part develops, the right-handed rotation, right-handed angular momentum, and this part, the left-handed rotation, left-handed angular momentum. So here in this condensed matter, let us define something like a helicity, like a momentum multiplied by the rotation, orbital plus spin. So in this chiral symmetric system, if TDDFT, if you calculate the TDDFT for this system, and if you calculate each eigenstate or total system, the helicity value, let's define helicity this way. Helicity will be zero. Helicity will be zero because the current in the same way, rotation will be opposite way, part by part. Esmaeil, do you understand what I'm talking about?
Yes.
Okay. Now let's think about the application of a magnetic field. Application of a magnetic field. You see that if you apply the magnetic field, this is the old calculation, and we discuss with this way, magnetic field up and the magnetic field down, and the different chiral. Let's think about chiral symmetric system. Chiral symmetric system, let's apply the magnetic field. In this case, this left part, right-handed rotation, the right part also right-handed rotation, but in this case, a linear momentum current will be opposite. So in this case, still let's calculate the helicity. helicity still will be summed up to 0. Do you understand or do you agree?
Mhm.
Okay. Ali, do you agree with my guess?
Uh, I'm a bit confused about the concept of chirality and helicity, okay? And my question is that when and by which sum rule we can connect maybe the chirality to helicity. For example, if you, for example, apply a chiral magnetic field rather than the linear magnetic field, how do you maybe uh, explain these results? Yeah, it is a bit complicated for me
Yeah.
now.
Yeah. Helicity is defined here. Here I suggest to calculate this momentum, linear momentum multiplied by angular momentum, either spin or orbital, or either the spin plus orbital, kind of a momentum times orbital, like a translation times rotation. Let's calculate this operator in the context of a condensed matter. So please remember that in this chiral symmetric system, let us please remember Esmaeil's page 12. In the classical field theory, the left helical, right helical always equivalent, but it is a broken quantum field theory, anomalous way. Let's think about this chiral symmetric system. When you apply electric field, helicity is preserved. Left helical or right helical always equivalent. When you apply magnetic field, helicity is still preserved. Let's say chirality is still preserved. But when you apply electric field, magnetic field together, electric field and magnetic field together, you see it this way. You please sum this one and this one. If you please, summation of this response and the summation of this response. So when we apply the electric field and the magnetic field together, let's say that when we apply the E dot B, now the helicity becomes a non-zero. Yeah, helicity becomes non-zero. Helicity becomes non-zero. And now the chiral symmetry is, let's say that the total helicity will appear and the chiral symmetry is broken. Uh, the uh, but here this but if we compare this chiral symmetry breaking with that of a quantum field theory, uh, this is the what the but breaking, we follows the equation of motion, but in quantum field theory, the chiral breaking is introduced anomalous way on the way of a quantization of the field. But they both are given by the E dot B. So the big question is, what is the nature of this E dot B? They do the very same role in this condensed matter and high energy physics, high energy neutrino physics. So anyway, we will perform the, let me see. Abo? Hello, Abo? So can we apply the magnetic field in our TDDFT machine? Yeah, also also calculate the magnetic field. So we will calculate the Esmaeil.
Yes.
What we will do in our laboratory, what we should calculate.
For this case?
Yeah. Do you see? Do you see this one?
Yeah.
What we will do in our laboratory? I think Oisok and the Abo will calculate this problem with the TDDFT. What kind of calculation we will do? Ismail, can you describe in this context?
Actually, I don't understand what you mean by this calculation.
Yeah, this calculation. Let me share again. Let me share again. So this problem. About what kind of a TDDFT simulation you want to do in this context? Mm. Yes, but what kind of system? Which system? Yes, here, please remember that here also calculated single wire. We also calculated this current. You see time, current, and the orbital angular momentum, spin angular momentum of this single wire. So let me call it this single wire as a chiral asymmetric system. Ismail, do you understand? Do you agree?
Yeah, I know, understand.
Yeah, now let's calculate the chiral symmetric system, two wire. You know, please look at please look at me. Look at me. Yeah, please, please look at me, this one. Left chiral wire, right chiral wire. This is a chiral symmetric system. And what is, so Abba, yeah, you are a smart guy. You are a smart guy. So you are the we will calculate the
Oh,
we will
sorry.
put the yeah.
Sorry, I understood what you mentioned, and I want to say that actually after our previous discussion about bringing two chiral material with different chirality, left-handed, right-handed together, and after our discussions, I searched for a real material, real platform that maybe shows this kind of different chirality feature, but unfortunately, I didn't find any paper. Actually, I mentioned that. Yeah, I mentioned that I already saw something, but I think I was wrong, and
It's reality is not a problem. Here we are just a physics principle. So let's start with a kind of a from the nature. Let's think of a chiral symmetric system. And Abba, 어디서? We will calculate this helicity. Nobody has we will calculate this helicity. Then you see this system, when you apply electric field, the total helicity will be zero. We will calculate this one by TDDFT calculation. Magnetic field helicity will be zero. You will calculate this TDDFT. But, only when you apply E field, B field together, then the helicity will not be zero. So what we will do is this time profile of a current orbital spin, but we will calculate the helicity of this chiral symmetric system by applying the electric field alone, magnetic field alone, and electric field, magnetic field together. We will calculate the helicity, and we will observe, we will present the very condensed meta version of the chiral symmetry breaking. But keep in mind that this chiral symmetry breaking is very analogous to the quantum field theory chiral symmetry breaking. Now the next question will be on the side of a quantum field, the Dirac fermion theory. What's the role of the gauge field? Not the gauge field, force field. That's okay. Do you understand what we're gonna develop? Yeah. Can you repeat our idea? What do you want to do? Yeah. Ah, Actually, not that correct. You know maybe let me try. In our code, in our TDDFT code, in the octopus code, nobody calculate helicity. We should modify our TDDFT code to calculate helicity. This one. Okay, first. And Esmaeil and Abo, can you answer that for this chiral asymmetry system, also calculate the current orbital spin. For this chiral asymmetry system, single wire, if you calculate the helicity, the helicity remains 0 or non-zero along this time profile. How do you guess?
Yes, because it is the multiplication of the current direction, actually the momentum and the sign of the angular momentum over spin.
So the helicity will be 0 or non-zero?
I guess will be 0 because of the.
Why? Will be non-zero. You know
non-zero?
Yeah. Think about it, just this one. You know this we both plot the left-handed, the right-handed, but only think about left-handed case. Current times orbital. Linear momentum. Current is a linear momentum. Orbital spin, they are angular momentum. And if you multiply think of this one. Yes, think of this one, chiral asymmetric system. The Oisok's calculation tells that, when you apply electric field, the system develops a current and the orbital, chiral asymmetric system. So the helicity will not be 0.
You mean for each isolated chain?
It's isolated chain, chiral asymmetric system.
Oh, okay.
Do you understand? Do you agree?
Yeah, actually, I thought you meant about the pairing of them.
Okay, good. Okay, good. But do you understand? Chiral asymmetric system, if you calculate the helicity, we will calculate the helicity. Nobody has calculated helicity. We will calculate helicity. Helicity will not be 0, okay? But if you calculate the chiral symmetric system, helicity will be 0 on the application of electric field. Helicity will be still 0 on the application of a magnetic field. We will calculate this system. And also we will calculate this one, E dot B. Helicity will be 0 or will not be 0? Abba? Total helicity, if you calculate this one, total helicity will be or will not be 0? Esmaeil, how do you guess?
As you mentioned, for both of them, when we have both electric field and magnetic field, we expect that it is non-zero. due to
Do
either.
you, yeah. Abo, do you agree? Yeah, we should calculate the helicity. And Ismail, would you share your page 12 again?
Yes.
Professor Park, can I
Yeah.
ask a question?
Yeah.
I'm thinking about octopus code, okay? How we can calculate the helicity. Uh, as far as I remember, the octopus code can separately calculate the expectation value of momentum and angular momentum, okay? Can I separately times these two ones to get helicity, or is it not?
Very good question. Very good question. Ismail, can you answer to Ali's question? So let me share. Ismail, let me share the screen. Yeah. Let me share the screen.
Yeah.
This is Ali. This is a very good question. A very good question. Uh, the question is you know the Do you see my screen?
Yes.
So what Ali is asking is that should we calculate this one, or should we calculate this one? Do you see my screen?
Yes.
Yeah. So Ali is asking that using the octopus, should we calculate this one, or should we calculate this one? So Ismail, can you answer how can it define the helicity? Which will be reasonable definition of helicity in the solid state context?
Actually, the up one,
Hmm.
but I cannot explain why.
Yeah, very good answer. Very good, very honest answer. I think this one. I think this one would be better definition. Definition of a helicity operator.
Actually,
I don't know.
Professor, sorry, I
Hmm.
have another question related to this one.
Yeah.
In quantum field theory, as I told in my presentation, the helicity concept is about that the parallel and antiparallel of the feature of the spin
Hmm.
and the momentum.
Right.
Here, what would be the concept of the helicity? If you want to explain when we consider the total angular momentum instead of a spin,
Right.
then
Right.
what would be the concept? I mean, I
So
don't have a sense.
yeah. My short answer is let us first define the helicity operator and let us physically interpret this one. Kind of a helicity, like massless Dirac particle helicity is that the momentum inner product, the spin. It is whether the spin is in momentum direction or in the opposite momentum. Here, let's think about the P jet, L jet, for example. Momentum is upward, and the angular momentum is upward. You know, this right-handed rotation, angular momentum is upward. So this is the momentum and the angular momentum is in parallel. This right-handed rotation is angular momentum up. And, this left-handed angular momentum is angular momentum down. So it is opposite direction to the linear momentum. So the interpretation is the same, I think. Do you agree or do you understand?
Yeah. I remember that Professor Benghai defined kind of an orbital polarization quantity. Can we say that the helicity here is the directional, the direction of the momentum, the linear momentum, and the orbital polarization?
The orbital polarization and the angular momentum is different. So here the thing is that
because this angular momentum is a dynamical version, so
dynamical version always everything I'm talking about is a dynamical situation, current flowing situation. It means that when there is always I am talking about this time profile. So everything is I'm not talking about static situation, everything in the dynamical situation. So okay. So I have a question. Mm. Yeah. Yeah. And anyway, do you still see my screen?
yes.
Yeah. Ali?
Yes, I see.
Yeah. To your question, I think I have the same opinion with the Esmaeil that we should define the helicity operator. So and in our TDDFT code and in the Octopus code, the helicity operator is not implemented. We need to upgrade the TDDFT code. You can do this one, but helicity operator is not defined. You can so yeah, this will be very important. Ismail,
Yes.
maybe you can try to work on your tight binding code. Do you think you can define the helicity operator in the tight binding code?
I think so, yeah.
Yeah.
Because
Yeah. So the thing is that again we will define the helicity as a new operator, and we will calculate the helicity of this chiral asymmetric system. And we also calculate the helicity of this chiral symmetric system. And let's observe the quantum field theory, the anomalous breaking of the chiral symmetry by E to fifth. Okay, yeah. I need to have a breakfast. Yeah. Sorry, I'm destroying your peaceful Friday weekend. So okay. So thank you.